Hello and welcome back to ABT. In this course we're going to be covering troubleshooting and calibrating VAV boxes. We're using version 1.2.1.6. I recommend that you review the files and folders, velocity, pressure, traverse, feet per minute traverse prior to watching this video. The first thing we're going to do is go ahead and activate ABT, and we're going to go ahead and set our directory. So if you go to the Start menu, in your programs, you have an ABT folder, and then you have a second ABT folder with your resources, student labs, and training. We're going to go into the student labs, shop lab test, comfort, commercial, and set our directory for our intro form. We'll go ahead and copy that and paste it. And now we can open our intro form HVACR Training Center 0004. So the next thing we'll do is go ahead and open up our Traverse VP form. We'll set that directory not to the commercial but to the test folder. So we'll go ahead and copy that, and as you can see it ends at commercial. That's the same file as the entry form. So go ahead and paste that into there, and now this file can start opening up these XML files. So the next thing we're going to do is go ahead and go back to our ABT folder, and in our resources folder we're going to go ahead and open up the VAV.pdf, and we will go to the internet, and we're going to look for K-factor for Titus. So this is a Titus manual for Aerocross for inlet sensor applications on all units except QCV, discharge sensor applications for dual ducts, and inlet sensor applications for QCV. So what is K-factor? This is, according to Titus, K-factor is the flow required to produce a 1-inch pressure drop in inches of water differential pressure on the Aerocross CFM. So they're talking about the CFM rating. So here's a CFM for these different size boxes. The differential pressure is a differential pressure on the Aerocross sensor. So then our CFM is equal to our coefficient K-factor, which is our CFM multiplied by the square root. So it's a CFM rating at a 1-inch pressure drop across this box multiplied by the square root of the differential pressure. So let's go ahead and take a look and see what that looks like. So in this case we're looking at a Titus inlet sensor 20-inch box. We've got a K-factor of 2106. So for a 20-inch box we have a K-factor of 2106, and we're going to multiply that by the square root of the differential pressure, which is 0.8. So we'll say 0.8, the square root of that, multiplied by 2106, and we come up with 1,883.6 CFM. And in this case we came up with 1,883 CFM. If we were at 0.5 we would get 1489, and let's say at 0.5 the square root of that multiplied by 2106, and we would get 1489. But in this case let's just say we're at 0.8, we're at that value. Text document. And let's take a look at the Johnson Controls literature, and in this case, in this file they say that the flow is equal to the area times 4005 multiplied by the square root of the velocity pressure divided by the pickup gain, and then the pickup gain is equal to the area times 4005 divided by the flow to the power of 2 multiplied by the velocity pressure. We're going to need to know the pickup or gain because we don't get that with the Titus file. So let's go ahead and go down to Titus, and here's Titus inlet sensor. Go ahead and go to the 20-inch, and it looks like the CFM matches and it looks like the area matches. 2106 and 0.778. 2106 and 0.778 for the area, and it's 2.19 for our K factor, or our constant in this case. They also call this gain. Okay, so let's go ahead and do this calculation. We're going to say 0.8 divided by 2.19 equals, I'm going to say the square root of this multiplied by 4005 equals, and then we're going to multiply that by 0.778. Now this calculation gives us the same calculation of 18.83 for a 20-inch Titus inlet sensor application with a K factor in CFM of 2106 with a differential pressure of 0.8. So now as we go down and we look at this calculation, we can compare that data to the outlet flow of the box. The outlet flow is going to be, our CFM is equal to 4005 times the square root of the velocity pressure times the area. It doesn't have to take into account the multiplier. So this way we can compare our reading to the output of the box, and we should get the same. Probably want to do this on your first box, but each additional box, once you know which box it is and you've compared your reading, you can actually use that equation for all other boxes you're getting ready to go through and calibrate. Unless you have to troubleshoot, then you might want to go ahead and do an outlet test. So let's take a look and see what that looks like. 1883 CFM moving across this box would have a change in pressure as it goes through the box. That change in pressure downstream is going to be a reading velocity pressure of 0.0465, which would actually equate to 1884 CFM based on a feet per minute change, obviously, as there is a pressure drop, and an area change. This particular duct, as you can see, that 20-inch box has a smaller area. It's got a 0.778 area, so it's actually less than 20 inches. It's quite a bit less, right? Because the area of a 20-inch duct is 2.18. This is why you can't, or in the past you couldn't use your magnehelic on a VAV box to calibrate or troubleshoot without having to do the equation. This tool does it for you. So let's take a look at another VAV box. And in this case, let's take a look at a 10-inch. It's 1436. So now let's do the math. If we had a 0.5 pressure drop across the sensor on a 10-inch, we divide that by the gain, which is 2.31, and we take the square root of that and we multiply it by 4005, and then we take that and we multiply that by the area, which is 0.545. That would give us a CFM of 1015, 0.49 or 0.5, and that's 1015.4. Okay, so now let's take that same equation. Let's take the differential pressure, 0.5, take the square root of that and multiply that by 1436 times 1436, and we came up with the same. So now let's go ahead and take a look at a different manufacturer box. And in this case, our next example is going to be test number 3, same job number, and this is going to be a Carnes cross flow sensor 14-inch. We've called this VAV number 3. So Carnes company's on page 4. So let's get the right file here. So in this case, Carnes cross flow sensor 14-inch, and we have Carnes standard, Carnes cross flow. Now we don't want to have to go back to a file to remember all these numbers, so we've made it easy for you. All you have to do is go to K factor, click on this button, and type in, since this is going to be VAV3, we'll call it VAV3, and we'll say Carnes cross flow 14-inch, and we have a 0.25. I'm going to go ahead and put 0.25 in there, and we'll calculate out, and it automatically knows that a Carnes cross flow has a K factor coefficient of 2908. We put in the pressure drop across the pickup tube, and we can read our 1454 CFM, which equates to that. Now if this were a 0.5 pressure drop, and as you can see we get an exception, so we'll go 0.5, and we'll say, okay, well, let's move this to the VP form, so make sure you're clicking the right box, and we can push that data right up to that form, and then we could actually close this out and save the file. But in this case we're actually working with a 0.25, so we'll leave it at 0.25. So we got a pressure drop of 0.25. We'll divide that by the gain of 2.1. We'll take the square root of that, and we'll multiply that by 4005, and then we'll multiply that by the box area, which is 1.05, and we come up with 1451, actually 9.4, so it's about 1451. And in this case we're getting 1454. So on the lowest end of the scale we can say 3 times 100 divided by 1454, and we're at a percentage of 0.2, which in most case sensors are plus or minus 2%, and we're at 0.2 at the lowest end of this scale. So let's go ahead and take another look at a different box, and in this case we'll just jump to 8, and on 8 we're looking for an EH Price single duct powered inlet box 6-inch. And dual duct. So we have dual duct and downstream flow. So we'll say dual duct 6-inch. In this case, again, we're at a 0.8 pressure drop. So we'll say this is VAV number 8. .8, and that would be about 423.38. If this were at 0.75, we could actually push that data up to there, but in this case we'll leave it at 0.8. We're going to do the same thing here for this particular box. So let's look for an EH price. EH price would be on page 9. So EH price, this would be single duct, fan power, parallel, and dual duct. Then we have for EH price we have dual duct downstream. In this case we're looking at this particular box. and it's a K factor of 470, differential pressure of 7.5. This box would actually be producing 470 CFM. Now we're going to go ahead and go to the traverse. We'll pull up our calculator. We'll do this calculation and we'll say 0.8. We'll go 0.8, the square root of that, multiplied by 470. We come up with 420, which is, I think, a lot easier calculation. But we'll go ahead and run the numbers, and we'll say 0.8 divided by 2.8. We'll take the square root of that, we'll multiply that by 4005, and then we'll take that and we'll multiply that by the area, which is 0.196. And we come up with 419.5. Now again, if we're just going and measuring a straight duct, it's 4005 times the square root of the velocity pressure times the area. When we're dealing with the VAV box, we have K factor that we have to deal with. The best equation is to say your CFM is equal to your known K factor in CFM multiplied by the square root of the differential pressure. Okay, say we run into a VAV box and we don't know who the manufacturer is and we don't know what the K factor is. The first thing we're going to want to do is we're going to disconnect the controller, press the release button and adjust the damper so that we're midway. We want to take control of the fan, increase or decrease the fan airflow so that we achieve a 1 inch, and then we'll lock the fan down, and then we're going to go ahead and measure the output of the box at that 1 inch pressure drop. Now say we measure 2400 CFM on the outlet of the box, and what we'll do is we're going to go to example number 11, and example number 11 is an unknown VAV box. We've recorded at 2400 because the outlet of our VAV box was 0.0755, and at 0.0755 went ahead and saved that, and we populated both our X and Y axis, and this is a 20-inch duct, so we saved that and we came up with 2400 CFM. So now the K factor at 1 inch is 2400 CFM. So now that we've recorded that and we know, okay, this is a 2400 CFM box, we'll go ahead and reconnect the controller, and we'll go ahead and release the fan so now it can control, and we'll take our reading at our maximum CFM cooling set point, and say our maximum cooling CFM set point, we recorded a 0.75. That would give us a VAV CFM of 2078 CFM. Now what we should see on the outlet to match that 2078 CFM, we'll go ahead and adjust the reading and see what it would be at 2078. At the outlet of the VAV, that magnet helix should read 0.0566 if it were an electronic device, but if it's a regular mag, we might read a 0.055, 0.056. I hope this helps you with troubleshooting and calibrating VAV boxes. Thank you for watching.